It is acceptable to have both the ground line from the meter and the ground line from the panel clamp onto the same ground rod. This configuration is acceptable because the ground rod provides a low resistance path to the earth, which is the ultimate goal of grounding electrical systems. Electricity does indeed take the path of least resistance. In this scenario, the path of least resistance is through the ground rod and into the earth. The earth is a good conductor of electricity, so it will effectively absorb and dissipate any current that flows through the ground rod. Let's delve deeper into how a grounding system operates. The electricity flows from the electrical panel through the ground wire, also known as the equipment grounding conductor, to the ground rod. The ground rod is then driven into the earth, providing a low resistance connection to the surrounding soil. From the ground rod, the electricity flows through the earth back to the electrical panel through the neutral wire, which is also connected to the grounding system. This grounding system plays a crucial role in protecting people and property from electrical shocks and fires. In the event of a fault in the electrical system, such as a short circuit or insulation breakdown, the electricity will flow through the ground wire and the ground rod instead of through a person or property that might come into contact with the energized circuit. To understand this better, let's break down the key components and principles involved. Firstly, the equipment grounding conductor is a safety wire that connects the metal enclosures of electrical equipment and appliances back to the electrical panel. This wire provides a low impedance path for fault current to flow back to the source, allowing the overcurrent protection device, such as a circuit breaker or fuse, to quickly trip and energize the circuit. Secondly, the ground rod is a conductive rod, typically made of copper or copper-clad steel, that is driven into the earth to provide a direct connection to the ground. The ground rod helps to dissipate fault current into the earth, reducing the risk of electric shock and minimizing damage to equipment. Thirdly, the neutral wire is a current-carrying conductor that provides a return path for electricity to flow back to the source. In a properly grounded system, the neutral wire is connected to the grounding system at the service entrance, which helps to maintain a stable voltage and prevent voltage fluctuations. Now let's consider some of the technical aspects of grounding. The National Electrical Code, or NEC, provides specific requirements for grounding electrical systems. These requirements are designed to ensure that the grounding system is effective and safe. The NEC specifies the size and type of grounding conductors, the depth and spacing of ground rods, and the methods for bonding different parts of the electrical system together. For example, NEC Section 250.52 outlines the requirements for grounding electrodes, which include ground rods, ground plates, and underground metal water pipes. NEC Section 250.66 specifies the size of the grounding electrode conductor, which connects the grounding electrode to the electrical panel. NEC Section 250.104 addresses bonding of metal water piping systems, metal gas piping systems, and other metal parts that are likely to become energized. In addition to the NEC requirements, there are also industry standards and best practices that should be followed when designing and installing grounding systems. These standards and practices can help to improve the performance and reliability of the grounding system and minimize the risk of electrical hazards. For example, it is important to ensure that all connections in the grounding system are tight and corrosion resistant. Loose or corroded connections can increase the impedance of the grounding path, which can reduce its effectiveness in clearing fault currents. It is also important to properly size the grounding conductors to ensure that they can carry the maximum fault current that is likely to occur. Undersized grounding conductors can overheat and fail, which can create a safety hazard. Furthermore, it is crucial to select the appropriate type of ground rod for the specific soil conditions at the installation site. Different types of ground rods have different resistance characteristics, and the selection of the wrong type of ground rod can significantly reduce the effectiveness of the grounding system. To further illustrate the importance of proper grounding, let's consider a scenario where the grounding system is inadequate or improperly installed. Suppose that there is a fault in an electrical appliance such as a refrigerator, and the metal enclosure of the refrigerator becomes energized. If the grounding system is not properly installed, The fault current may not flow back to the electrical panel quickly enough to trip the circuit breaker. As a result, the metal enclosure of the refrigerator may remain energized, and anyone who touches the refrigerator could receive an electric shock. However, if the grounding system is properly installed, the fault current will flow back to the electrical panel through the ground wire and the ground rod, causing the circuit breaker to trip and de-energize the circuit. This will prevent the metal enclosure of the refrigerator from becoming energized, and it will protect people from electric shock. In summary, it is acceptable to have both the ground line from the meter and the ground line from the panel clamp onto the same ground rod. This is because the ground rod provides a low resistance path to the earth, which is the ultimate goal of grounding electrical systems. Electricity does take the path of least resistance, and in this case, the path of least resistance is through the ground rod and into the earth. A properly installed and maintained grounding system is essential for protecting people and property from electrical shocks and fires. It is important to follow the NEC requirements and industry best practices when designing and installing grounding systems to ensure that they are effective and safe. Now let's discuss the specifics of the 6 American wire gauge copper ground line. American wire gauge, abbreviated as AWG, is the standardized wire gauge system used predominantly in the United States for the diameters of round, solid, non-ferrous, electrically conducting wire. The larger the American wire gauge number, the smaller the wire. A 6 AWG copper wire is a relatively thick wire, and it is commonly used for grounding applications because it is a low resistance and can carry a large amount of current. Copper is an excellent conductor of electricity, and it is also corrosion resistant, making it a good choice for grounding conductors. The NEC specifies the minimum size of grounding conductors based on the size of the overcurrent protection device protecting the circuit. For example, NEC Table 250.122 provides the minimum size of equipment grounding conductors for grounded systems. If the overcurrent protection device is rated at 60 amps, the minimum size of the equipment grounding conductor is 12 AWG copper or 10 AWG aluminum. If the overcurrent protection device is rated at 100 amps, the minimum size of the equipment grounding conductor is 8 AWG copper or 6 AWG aluminum. If the overcurrent protection device is rated at 200 amps, the minimum size of the equipment grounding conductor is 6 AWG copper or 4 AWG aluminum. In the case of a 6 AWG copper ground line, it is likely that the overcurrent protection device protecting the circuit is rated at 200 amps or less. However, it is always important to verify the size of the overcurrent protection device and the NEC requirements to ensure that the grounding conductor is properly sized. In addition to the size of the grounding conductor, it is also important to ensure that the grounding conductor is properly installed. The grounding conductor should be securely connected to the ground rod and to the electrical panel. The connection should be tight and corrosion resistant to ensure that the grounding path has a low impedance. The grounding conductor should also be protected from physical damage. If the grounding conductor is damaged, it may not be able to carry the full fault current, which could create a safety hazard. Furthermore, it is important to ensure that the ground rod is properly installed. The ground rod should be driven into the earth to a depth of at least 8 feet, and it should be located in an area where the soil is moist and conductive. The ground rod should also be protected from physical damage. If the ground rod is damaged, it may not be able to provide a low resistance path to the earth, which could compromise the effectiveness of the grounding system. To summarize, a 6 AWG copper ground line is a common choice for grounding applications because it has a low resistance and can carry a large amount of current. However, it is important to verify the size of the overcurrent protection device and the NEC requirements to ensure that the grounding conductor is properly sized. It is also important to ensure that the grounding conductor and the ground rod are properly installed and protected from damage. Let's also discuss the concept of earth-absorbing power. While it's common to say the earth absorbs electricity, it's more accurate to say it dissipates electrical energy. The earth acts as a vast reservoir and a relatively good conductor, allowing electrical current to spread out over a large area. This spreading out of current reduces the electrical potential, essentially dissipating the energy. The Earth's ability to dissipate electrical energy is due to its composition and moisture content. Soil contains minerals and water, both of which can conduct electricity. The conductivity of the soil varies depending on its composition, moisture content, and temperature. Moist soil is a better conductor than dry soil, and soil that is rich in minerals is a better conductor than soil that is poor in minerals. The Earth's ability to dissipate electrical energy is also affected by the presence of underground utilities such as water pipes and gas pipes. These utilities can provide a path for electrical current to flow through the Earth, which can increase the risk of electric shock. Therefore, it is important to be aware of the location of underground utilities when digging or working in the ground. To further illustrate the concept of Earth absorbing power, let's consider a scenario where lightning strikes the ground. Lightning is a massive discharge of static electricity, and it can deliver a huge amount of energy to the Earth in a very short period of time. When lightning strikes the ground, the electrical current spreads out through the Earth, dissipating the energy. The path that the current takes through the Earth depends on the conductivity of the soil and the presence of underground utilities. If the soil is moist and conductive, the current will spread out more quickly and evenly. If the soil is dry and poorly conductive, the current will be more concentrated, which can increase the risk of electric shock. The Earth's ability to dissipate electrical energy is also affected by the presence of trees. Trees can act as lightning rods, attracting lightning strikes to their branches. When lightning strikes a tree, the electrical current travels down the trunk of the tree and into the earth. The roots of the tree help to spread out the current through the earth, dissipating the energy. However, if the tree is located near a building or other structure, the lightning current can also flow through the structure, which can cause damage or fire. In summary, the Earth's ability to dissipate electrical energy is due to its composition, moisture content, and the presence of underground utilities. The Earth acts as a vast reservoir and a relatively good conductor, allowing electrical current to spread out over a large area. This spreading out of current reduces the electrical potential, essentially dissipating the energy. While the term absorb is commonly used, dissipate is a more accurate description of the process. Finally, let's discuss the path of least resistance in the context of grounding systems. Electricity always seeks the path of least resistance. This means that when there are multiple paths available for electricity to flow, it will choose the path that offers the least opposition to the flow of current. In a properly grounded electrical system, the grounding path provides a low resistance path for fault current to flow back to the source. This low resistance path ensures that the fault current will flow quickly and safely back to the source, tripping the overcurrent protection device and energizing the circuit. The resistance of the grounding path is determined by the size and type of grounding conductors, the quality of the connections, and the conductivity of the soil. The larger the grounding conductors, the lower the resistance. The tighter and more corrosion-resistant the connections, the lower the resistance. The more moist and conductive the soil, the lower the resistance. If the grounding path has a high resistance, the fault current may not flow quickly enough to trip the overcurrent protection device. This can create a dangerous situation, as the fault current may flow through other paths, such as through a person or through a building structure, which can cause electric shock or fire. Therefore, it is important to ensure that the grounding path has a low resistance by using properly sized grounding conductors, making tight and corrosion-resistant connections, and ensuring that the soil is moist and conductive. To further illustrate the concept of the path of least resistance, let's consider a scenario where there is a fault in an electrical appliance, such as a toaster. If the toaster is not properly grounded, the fault current may flow through the metal enclosure of the toaster and through a person who touches the toaster. This can cause a severe electric shock. However, if the toaster is properly grounded, the fault current will flow through the ground wire to the ground rod and back to the electrical panel. This low resistance path will allow the fault current to quickly trip the circuit breaker, to energizing the circuit and preventing electric shock. In summary, electricity always seeks the path of least resistance. In a properly grounded electrical system, the grounding path provides a low resistance path for fault current to flow back to the source. This low resistance path ensures that the fault current will flow quickly and safely back to the source, tripping the overcurrent protection device into energizing the circuit. It is important to ensure that the grounding path has a low resistance by using properly sized grounding conductors, making tight and corrosion-resistant connections, and ensuring that the soil is moist and conductive. Considering everything, the practice of connecting both the meter and panel ground lines to a single ground rod is acceptable and promotes electrical safety. It is important to consult with a qualified electrician to ensure that the grounding system is properly installed to meet all applicable codes and standards.